Suppose we have a universe without life, including human. The question is following: what is more complicated, a universe without life, more complex, or one man, or one simpler organism?
Well, I suppose even the young Earth, the Earth when it was young was quite complicated, very complicated geology and chemistry. So once you have the periodic table of elements made in stars, then even the inanimate structures you can form, like planets, are quite complicated. So even if there was no life on the Earth would be still quite a complicated system.
Yes, please.
Everything is as complicated as what you want to say about it. You know, and if you can say, if you talk about the planets and you say the orbit is a level of complexity, and if you want to say the composition is another level, and with any subject in everyday life, you know, there is like a hierarchy of models to try to describe reality, and depends how deep do you need to understanding. You know, it's like fluid dynamics is a good example where you can look at fluids in many different scales and with different complexity.
Yes, but I think you could say in an objective way that a planet which has a differentiated structure and most of the periodic table in it is more complicated than, say, a young star, which is just hydrogen and helium and amorphous structure. So I think you can say in some respects that objectively a planet is more complicated than a star, and of course the simplest life is more complicated than most inanimate systems.
You had some questions?
I would like to know, you know, you have now an understanding of the beginning, wherever it is, that beginning is, and then you have the first moments, and then you have an evolution, and then you have the present state of the universe. There is a complexity characterization for the different phases. Is there something being done to what is this kind of a characterization? And is there an index, for example, of the complexity itself, the way in which the universe has evolved?
Yes. Well, as I say, we can go back with some confidence to a nanosecond, but we believe that the intrinsic features of the universe, its expansion rate, the fluctuations, and the asymmetry between matter and antimatter are imposed much earlier on when the temperatures equivalent, say, 10 to the 15 GeV. And there we have no direct empirical knowledge. We have to await the next step in theoretical physics and some indirect tests. And of course, to be more speculative still, there is strong reason for suspecting that the visible universe, which we can see as the limit of our telescope, is not all of physical reality. Everyone would, I think, accept that there are many galaxies which are far beyond the range of our telescope because the light hasn't had time to reach us. But that is the aftermath of our Big Bang. There is also the idea that our Big Bang was not the only one, that there is a sort of multiverse of Big Bangs, and then that raises the other question, are the fundamental physical laws, which are the same in all the parts of the universe we can observe, the same in every galaxy, are those laws the same in this grander perspective, or do different Big Bangs cool down, governed by different fundamental laws? This is something which is a consequence of some theories, the so-called landscape string theory, but we don't know at all. But as we extend our horizons, then we suspect that a further Copernican demotion may confront us, in that we're used to the idea that our solar system is not the only one, our galaxy is not the only one, and maybe our Big Bang was not the only one either.
Okay, we can take as a message from several of these presentations that science is by far not at the end. So future generations of scientists will still have interesting questions to deal with.